Welcome. In this video, we will explore log-based recovery, a crucial technique for ensuring data durability in database systems. We will focus on how transaction logs are used to recover a database to a consistent state after a failure. The subtitle is Using Transaction Logs for Database Recovery. Let's begin by understanding what transaction logs are. Transaction logs are a sequential record of all modifications made to the database. They contain before and after images of the data, which allow us to revert back to the original state if needed. They include timestamps for transaction operations, providing a timeline of events. Transaction logs are critical for ACID compliance, specifically ensuring durability, meaning that once a transaction is committed, it remains so, even in the event of power loss, crashes, or errors. Now let's look at some example log entries. We have transaction 1 starting, then a write operation on data item A, changing it from 100 to 200. Next, another write operation on data item B, changing it from 50 to 25. Finally, transaction 1 commits. Following this, transaction 2 starts. There are 4 main types of log records. First, we have the transaction start record. This marks the beginning of a transaction with a unique identifier. For example, T1 start. Next, there are update records. These record data modifications with the before and after values. For example, T1 write a old value, new value. Then we have commit records. They indicate the successful completion of a transaction. For example, T1 commit. Finally, there are abort records. They indicate a transaction failure and the need for a rollback. For example, T1 abort. Write-ahead logging, or WAL, is a protocol that dictates the order in which operations are performed. The WAL protocol ensures that all changes can be recovered in the case of system failure. Let's see the principles behind it. First, log records must be written to stable storage before the corresponding data pages are modified on disk. Second, the transaction commit record must be written to the log before the transaction is considered complete. Let's look at the write-ahead logging process flow in the diagram. Starting with the transaction, we have the log buffer. Data flows from the transaction to the log buffer. The first step. Next, the log buffer is written to the log file. Second step. From the log buffer, data also goes to the data buffer, the third step, but this happens after writing to the log file. And finally, the data buffer is written to the data file. The fourth step. The write-ahead logging rule is log first, data later. Now let's discuss checkpoints. Checkpoints reduce recovery time by limiting how far back the system must scan logs. It ensures all committed transactions changes are written to disk and records active transactions at checkpoint time. It also allows for efficient buffer management and log truncation. Here is an example of a checkpoint log. We start with transaction 1 starts, transaction 1 writes A from 100 to 200, transaction 2 starts, transaction 2 writes B from 50 to 75, transaction 1 commits, then the checkpoint listing transaction 2 as active. Following this, transaction 3 starts, transaction 2 writes C from 30 to 10, transaction 3 writes D from 40 to 60, and then transaction 2 commits. The recovery process consists of 3 phases: analysis, redo, and undo. During the analysis phase, the system identifies transactions that need to be redone or undone. This involves finding the last checkpoint in the log and identifying active transactions at that time. Then the redo phase. This reapplies all updates from committed transactions. This involves replaying all updates from the last checkpoint to ensure that all committed work is durable. Finally, the undo phase. It reverses the effects of incomplete transactions by rolling back uncommitted transactions and writing compensation log records. The recovery timeline diagram shows the checkpoint, the system crash, the analysis phase, which starts at the checkpoint and goes up to the system crash, the redo phase, which also starts at the checkpoint and goes up to the system crash, and the undo phase, which starts somewhere in the middle and ends at the point where the recovery is complete. ARIES stands for Algorithm for Recovery and Isolation Exploiting Semantics. Let's explore its key principles. First, write-ahead logging. Log records are written before data changes. Second, repeating history. Redo all operations since the last checkpoint. Third, LSNS. Log sequence numbers uniquely identify each log record. Fourth, page-oriented redo. Updates are applied at the page level. Fifth, logical undo. Uses compensation log records. Here is the ARIES pseudocode. The ARIES recovery function includes the analysis phase, finds the last checkpoint, gets active transactions, and gets dirty pages. The redo phase gets the minimum record LSN from the dirty pages and redo updates from that point. And finally, the undo phase undoes incomplete transactions. Let's see a few optimizations that can be used in log-based recovery. Fuzzy checkpointing allows checkpoints without freezing transaction processing. It records dirty pages without forcing writes and minimizes system disruption during checkpoints. Group commit batches multiple transaction commits into a single input-output operation. This reduces log input-output overhead and improves throughput for small transactions. Log compression reduces log size by eliminating redundant information. It stores only net changes for frequently modified data, and it decreases storage requirements and input-output time. Parallel recovery utilizes multiple threads for faster recovery processing. It parallelizes redo and undo operations and reduces recovery time for large databases. Let's quickly summarize the key takeaways from this video. Transaction logs provide a sequential record of all database modifications and are essential for recovery. Write-ahead logging or WAL ensures durability by writing log records before data changes. Checkpoints reduce recovery time by limiting how far backlogs must be scanned. The recovery process involves analysis, redo, and undo phases to restore database consistency. And finally, ARIES provides a robust framework for efficient database recovery. Following this topic, you might be interested in learning about shadow paging recovery, concurrency control, distributed database recovery, and high availability solutions. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.